Welcome to my YouTube channel. This is Uncle Pythagoras signing in. Today we are going to deal with the increasing, decreasing functions by using the first derivative, the concavity and the inflection points by using the second derivative. This is where the function increases. When the function increases, the first derivative is positive. When the function decreases, the first derivative is negative. When f is constant, the first derivative is equal to 0. This happens when our tangent is horizontal to the function, to our graph, is horizontal to the curve. For example, let's say we have a curve like that. This curve, the first derivative is positive. So the function increases at this point. Here at this point, we have a maximum local. At this region, our first derivative is negative and our function decreases. When we get at this point, we have our minimum local point, and at our minimum local point, our f, the first derivative, is equal to 0, and here the first derivative is equal to 0. Now if you check here, we have our first derivative to be positive and our function increases. We are going to see more and more of this nature as we go through the problems and the examples together. Now, this point here is called a critical point. This is where we find our critical point. Some people call it a critical number or critical value. Critical value occurs when our f dash is 0. The critical value occurs when the first derivative is equal to 0, or rather let's look at on this point, this fact. When the first derivative is equal to 0, that's where we find our critical value. Let's take for example, we have f at x is equal to x cubed minus 3x squared. Okay, in this case, we have to establish the fact that the function increases, the function is at the maximum point, the function and minimum, and the function increases. So we are going to see all that by using the f at x equals to x to the power 3 minus 3x squared. Right, let's find our first derivative. Our first derivative is equals to 3x squared minus 6x. At some point, this is equal to 0. This is a critical, what we are talking about, the critical point where we find our maximum and minimum local point. So at this point, our function, our first derivative is equal to 0. Now, if we find the value of x, let's say we take out the common factor of 3x, here we are left with x minus 2 is equals to 0. Now the value of x here is x is equals to 0 or x is equals to 2. Now our technique here, we need to find out whether it is increasing or it is decreasing, or it's a minimum or it's a maximum local point. Alright, first thing, we are going to perform what we call the first derivative test. Derivative sign test. We set our x is 0 and our x is 2. Right, we are going to use f dash x, which is 3x of x minus 2. Now, if we substitute the value of x in this derivative, we must find out what does the sign of f at x turn into. Now, if we put 0 here, 0 multiplied by 3 is 0. X, if we put a 0 here, we're going to say 0 minus 2, which is minus 2. So here we have a negative sign. If we take any number between 0 and 2, say for instance 1, we put a 1 here, 3 times 1 is 3. A 3 is a positive sign. 1 minus 2, you have a negative 1. A negative times positive is negative. Let me check the first one here. Our first one, if we put a negative we don't include this. So my apologies, I included 0 here. We don't include 0. You take any number before 0, which is -1. You put a -1 here, a -1 multiplied by 3, you get a minus, and a -1 minus 2 is -3. A negative times negative becomes positive. So our sign is positive there. You come here, you take a number between 0 and 2. Let's say, for instance, you take a 1. A 3 times 1 is 3. A 3 is positive sign. A 1 minus 2 is -1. A negative times positive is negative. You go, you do the same thing. You take a number just after 2. Say, for instance, 3. A 3 times 3 is 9. 9 is positive. A 3 minus 2 is 1. 1 is positive. A positive times positive is positive. Now, this is our critical value. This is our second critical value. When you move from positive to negative, you are decreasing. Right? And our graph stays like that. We have a max, a maximum local point, here from negative to positive, it's facing upwards. We have our minimum. So the critical values here is 2, 0 and 2 are our critical values. So this tells us what? This tells us the interval our function here is increasing because our f dash is positive, so the function here increases. Our f dash here is negative. Then what happens if you take any number towards the negative x-axis? You will find that the function is increasing. So the function increases at the interval of negative infinity to 0. Union means end. From 2 to positive infinity. Another argument can come. Mathematicians are too specific. This interval here needs to be specified. If we specify it, we mean that 0 is exclusive, 2 is exclusive in this interval, because when you include this and that, everything falls apart. For the function decreasing, the interval is 0 between 0 and 2. 0 and 2. this is what we find about the first derivative sign test. Now, if we go forward, we come to talk about concave, concavity, and inflection. Concavity and inflection. Right? We are going to use the second derivative to find the concavity and the inflection. We take the first derivative. Our f at x first was x cubed minus 3x squared. We find the first derivative. It was 3x squared minus 6x is equal to 0. Now we go for a second derivative. The second derivative is going to be 6x minus 6. At some point this is equal to 0. Now we find the value of x. 6x minus 1 is equal to 0. It means that x is equal to 1. Right. At some stage, you don't say at 1 that's where the inflection takes place. You just say at x is equal to 1 is a possible. It's a possible inflection. Or you can say it's the English word that they like to use here is called, they say it is a potential. At x is equal to 1 is a potential inflection point. Now, what does this mean? This means that if we take a sign test, a second derivative, we find that this is 1. You take any number just before 1, which is 0. You put a 0 here, you find that 0 minus 1, you get a positive. You put a 2 minus 1, you get a positive here. Then, we can conclude by saying, at this point, the concavity is down, the concavity is up. This stands for concavity. Concavity is up at what intervals? It's up at what? At 1 to positive infinity. The concavity down is happening at negative infinity to 1. Then we can conclude now to say that now this is not a potential anymore. We are sure that at x is equal to 1, then inflection occurs. It occurs at 1 because we have obtained or we have proven that the change of concavity takes place. When the concavity does not take place, then there is no inflection point. We will see the next videos as we go through the previous question papers to check the examples to see how we go about solving the problems. Uncle Pythagoras signing out. Do not forget to like and subscribe. Thank you very much.